In this tutorial, I'll show you how to define the deformations our mesh can undergo. So we go from a static mesh to a model that defines deformations on this template, which we can randomly sample from to visualize it. Hi, and welcome to Coding with Dennis. My name is Dennis, and this here is the fourth tutorial in the series on how to create statistical shape models. Defining the deformation space that the template can undergo might seem daunting at first, with the endless possibilities of combinations. With a few heuristics in mind and a clear plan for defining your kernels, this task becomes a lot easier. For simplicity of this tutorial, I will not go into the formal definition of kernels. For this, I suggest you take a look at the tutorials from the Scalismo website or the instruction video from the Statistical Shape Modeling course at the University of Basel. In this tutorial, we'll mainly look at the Gaussian kernel and how we can modify it to, for instance, be symmetric around a defined axis using the Symmetry Kernel, only active in certain areas using the Changepoint Kernel, how we can mix Gaussian kernels with different properties. Finally, I'll show you the PCA kernel as introduced in the first video and how we can make it more flexible by augmenting it with an analytically defined kernel. Of course, many more kernels exist than just the Gaussian kernel, but I often find mixing different Gaussian kernels sufficient instead of using other kernel types. For the Gaussian kernel, we have two parameters to set. The first, the sigma value, defines the width of the kernel. The smaller the value is, the more local it is, meaning that only the very close points will have a covariance over 0. The second parameter is the scaling parameter. This can be used to adjust the strength or the amplitude of the function. So let's define this in code and set a sigma value of 100 and a scaling value of 1 to begin with. One thing we need to remember when working with kernels is the dimensionality we work with. I'll only show 3D examples, where it would also be possible to model the covariance between dimensions. But for simplicity, we always assume that the 3 dimensions are independent when analytically defining kernels. With the kernel defined, we use it to define a Gaussian process, which we'll use later for regression purposes. The Gaussian process that we have defined is continuous, but we're actually only interested in its values at the positions of our reference mesh. We can try to sample random deformations from the model and then use an interpolator to describe the deformations at the point of the reference mesh. Internally, the sample at point creates a huge covariance matrix. So, depending on your memory, you might need to decimate the mesh first to get the code snippet to work. We can get around this problem by approximating the covariance matrix instead of explicitly calculating it. The relative tolerance here specifies the approximation error that is allowed. Usually a value around 0.01 is desired, but to begin with, I often put a much higher value like 0.5 or 0.1 to quickly calculate the function and visualize it. The interpolator to use very much depends on your application. Either the nearest neighbor interpolator or the triangle mesh interpolator are good choices to try out with. And now with a low rank function, we should be able to sample without having to decimate our reference mesh first. And now an even more convenient way to visualize samples from a Gaussian process is to build a point distribution model from the low rank Gaussian process. This allows us to directly sample meshes that follow the distribution represented by the Gaussian process and not have to deform the reference mesh manually from the given informations. A point distribution model can also be viewed directly in Scalismo, and we have access to all its parameters as well as a handle to sample from the model randomly. After having found the correct parameters to use for the model, it can be stored in a file and directly read again from disk to avoid computing the model when we use it in the following tutorials. The native shape model format in the newer Scalismo versions are H5 JSON, which externally can be converted to an H5 file to save space. Scalismo can both read in the H5 JSON as well as the H5 format itself. When inspecting the model here, it's important to remember what the model will be used for. Our goal is to make the model flexible enough to represent all the other shapes in our dataset. This also means that when we randomly sample from our model, it is perfectly fine that deformations look exaggerated and produce non-natural shapes. The most important part is that the deformations are smooth, such that the mesh does not intersect with itself. This also means that, for instance, the mesh that we see here is far from flexible enough to represent other meshes, as it mainly just shifts the position of the mesh around. For the sigma value, I like to use a value that is half or 1/3 of the longest distance in the mesh. By looking at the scene view in Scalismo, we can get a feeling of the size of the mesh. Here we see that the mesh is 65 millimeters on the x-axis, 77 millimeters on the y-axis, and 39 millimeters on the z-axis. With the current value of 100, this means that all points will have some correlation, which will end up practically meaning that the deformations will translate the mesh around. Let's instead try to set the sigma value to 35. Afterward, we can tune the scaling value if the magnitude of this deformation is not large enough. I would recommend starting out with a simple model like this with a simple Gaussian kernel and then only making it more advanced if needed. And how do you know if more is needed? Well, if the model has problem representing the meshes in your dataset, then more is needed. For instance, if some local curvatures are not nicely captured, but you'll only get to know so after running the non-rigid registration as introduced in the next video. For completeness of this video, let's continue adding some local deformations to our model by combining a kernel with a large sigma value and one with a small sigma. For instance, a global and a local kernel. Here I typically like to visualize each model separately first, and then only afterward combine the kernels. An alternative kernel is the Symmetry Kernel. To showcase this kernel, I'll use the reference mesh from the Basel face model. First, let's look over how a random sample from the face model looks like with a kernel where we have sigma 100 and scaling 10, and then put this into a diagonal kernel. Afterward, in the Symmetry Kernel, we'll define the mesh to be symmetrical around the YC plane. Of course, in reality, faces are not fully symmetrical, but it's a good global kernel to have, and then we can afterward add local deformations to it. We create our own Symmetry Kernel by adding up two diagonal kernels, where one is the Gaussian kernel itself, and the other is a mirrored kernel that we then need to specify as an extension of the PD kernel. Here we simply provide the negative value of the x-axis. And now by randomly sampling from the model, we see that the deformation stays symmetrically around the YC plane. Another useful kernel is the Changepoint Kernel. For this, let's stick with the face mesh and make one side of the face with one kind of kernel and the other side with an inactive kernel. In this way, we should see that only half of the face deforms when we sample from the model. To do so, let's make use of a kernel function that extends the matrix value PD kernel, which implements the kernel function k. We provide here two kernels to the function, one for the active area and one for the inactive area. So for the inactive area, we just set a scaling value of the Gaussian kernel to 0. Make note of the S function, which defines the kernel to choose. This can be either binary to fully activate a kernel in a certain area and fully deactivate it in another, or it can be made smooth as in the given example, so that the two kernels will have a smooth transition around the x-axis in this example. And again, we check the model by visualizing it and randomly sampling from the model. We should now see how only one side of the face deforms. The final kernel I want to show is another mixture of kernels. This kernel could, for instance, be used to iteratively include more data into your model. We start out with 10 vertebra meshes that are registered. From this we can create a PCA kernel, as also shown in our first video. Of course, 10 principal components rarely contain all small possible deformations. So we can augment the model, for instance with a Gaussian kernel, to make it more flexible and add local deformations to it. Now when we sample from the original model in comparison to the augmented model, we see that a lot of more fine detailed deformations are available in the augmented model. And that's the end of the practical guide to choosing your kernels and hyperparameters. Really, the most crucial part is visualizing a model at every step of the way. Also remember to look at the official Scalismo tutorial on Gaussian processes and kernels, as the kernels are introduced there as well. In the next tutorial, I'll show you how to use this model we created to fit to a target, also known as non-rigid registration. That was all for this video. Remember to give the video a like, comment below with your own shape model project, and of course subscribe to the channel for more content like this. See you in the next video.